Hello. First off, I'm no YouTuber, so this isn't going to be some three blue, one brown amazing video. This is just some guy who likes to play with prime numbers in his spare time. Yeah, it seems like I've found something that could be interesting. It's involving the golden ratio and the density of prime numbers. So yeah, let me just show you the formula. There it is. Yes, n over ln n minus 1 is in here. I'll explain why a little later. So yeah, let's plug in a number. Let's make n 371. And we get how many primes are less than 52,576. We multiply those together and divide by 2. Now, the answer of how many primes is less than this using ln n minus 1 equals that. If we add this golden ratio stuff, we get a little higher estimate, and the actual number is that, 0.99. Now, you may think this is just a coincidence. I've tried many numbers, and it seems to work great. So let's try a higher number, 5,828. So how many primes are less than this 12 million number? Add those, multiply those together and divide by 2. So now with ln n minus 1, you get this result. If you use the golden ratio with it, you get this result, and there is the actual result. So you can see a big improvement there, 0.998. So yeah, you may think this is just a coincidence, but yeah, the golden ratio seems to work really well. So let's try changing the golden ratio to see if that makes any difference. So if we minus 0.1 from the golden ratio to make it just 1.6 instead of 1.618, we'll get how many primes are less than that. That's how many primes are actually below that, and that's the number we get using just 1.6. 0.95 away, and much lower. If we add 0.1 to make the golden ratio 1.63, that's the new number we get. How many numbers are less than that? That's the real answer, and that's the number we get using 1.63, 0.97, way over. Well, not way over, but not as good. So how I came across this, I don't even understand it myself, really. So I'm just going to give you a step-by-step of what I went through to get to this point over the last few months. So it all started a couple of months or a couple of years ago when I noticed that if you add the prime numbers, so 2 plus 3 plus 5 plus 7, up to n, that equals the amount of primes less than n squared. So, for example, 2 plus 3 plus 5, all the way up, add all the primes up to this big number, you get this huge number. Now that number squared gives you this huge number, and that's how many primes are less than it. As you can see, it's very close. I actually messaged Dr. James Grime of Numberphiles on this, and he responded and said, yeah, that's an actual thing, and it was discovered in 1996. 30 years ago in the math world is like yesterday, and I was pretty excited about that. So yeah, I played around with this idea for years, and I try to visualize it. So here's the sum of the primes, there's the square at the end. Eventually I realized you could put this inside the square. And then I realized you can push these all down and make a triangle. Now this is a geometry problem, which is a lot easier. So instead of adding them all you need to know is the prime, the nth prime, and the prime, divide by 2, and that equals the amount of primes less than prime squared. There's the formula. And yeah, I plugged it in for 1,517. I got that. There's how many primes are less than that, and yeah, it's pretty accurate, 0.93. So a little while later, I was playing around with these numbers. You have your 1, 2, 3, 4, 5, and then you have your multiplying by the primes. And you get these. These are actually very interesting numbers. A lot of cool things you can do with them. And I realized that this number you get at the end here is very similar to the amount of primes less than the first number squared. So for example, 7 times 17 is 119. 7 squared divided by 2 equals 24. The amount of primes less than 119 is 30.8. Now this, like everything else, gets a lot better the bigger it gets. So at 100, the 100th prime is 541. You get that. 100 squared divided by 2, you get that. How many primes are less than 54,100 is that, 0.9. And as you can see, I used a lot bigger numbers, and the approximation gets a lot better. Now it's 0.94. Then I realized this is also can be represented in a shape and just use simple geometry to solve. So yeah, now you get an isosceles triangle with a rectangle. Okay, so here's your nth squared divided by 2, and there's your nth prime divided by your prime. Then I remembered about my first shape, and then I realized I have now 2 shapes with similar properties, and I thought I'd better compare them and their properties. So yeah, I started using the same number for both. So yeah, the 178th prime is 1091. You times them together and divide by 2, take that, square it. As you can see, it's pretty close, 0.92. That's the real number. Here's the real number compared to that. It's pretty close, 0.92. Once again, it gets better the higher numbers we use. Here's a 2,200th prime is 19,423. Here's the result. There's the result, 0.94. Here's the result if we do it this way, 0.93. And that's when I realized these ones are always overestimating, and these ones are always underestimating. And almost by very similar margins too. 9292, 9493. So I have to combine these two somehow, and maybe I'll get a much better approximation. So yeah, obviously I just times them together and divide by 2, but that didn't work. And the reason that didn't work is because this number is a lot less than this number. Now what you need to do is visualize this shape morphing into this shape. So this triangle would move along here and get bigger and bigger, and this rectangle would become more and more square-like. This is almost like the minimum, and this is almost the maximum. But where does the triangle stop? And that's when I realized it's going to stop around here. And that line, compared to the long line, is the long line to the short line of the golden ratio. So obviously I plugged in the golden ratio. And this is the actual calculation I used. I took 2,200, and its prime is this one. And I broke it into its golden ratio numbers. Took the small side, divided by 2, got that. Took the big side, squared it. How many primes are less than that? There you go. Look how close that was, 0.996. Obviously I was super excited. That's how you can generalize it, by putting the triangle back in there. You can see there's the A, there's the B, there's the nth prime, etc., etc. So yeah, obviously I needed to try this for numerous numbers. And yeah, I used some small numbers. So the 178 prime is 1061, the short side, the long side, times them together, divide by 2, got that. Square the long side, and yeah, it was almost exact, 0.999. Use some bigger numbers. So here's 50,505. Its prime is here. Took the short side, times together, divide by 2. Got that number. The actual number below of primes below that number is very close, 0.993. Now, obviously you can see it's tending up just a little bit over. Still closer than n over ln minus 1, but it is creeping over. So that's what I decided, just to combine the two and see what happens. So yeah, here's a really large result, combining them together. And we take n and use this number, 641,894. We get this huge number. The actual amount of primes less than that is that. Now, if we just use n ln n minus 1, you get that, pretty close. But if you add the golden ratio, you get a much, much better approximation, 0.9997. Now, does this have some sort of underlining connection between the golden ratio, E, and the density of primes? I have no idea. Is this just a neat trick? Maybe, but we have found E in Pascal's triangle, and maybe the prime densities is somewhere in the spiral. Thanks for watching. If you have any input, I would love it. If you want to be able to put this on a computer somehow, I'd love that too. Thanks. Bye.